Every map of our solar system you have ever seen is a lie. Not a malicious deception, but a lie of convenience, a necessary fiction to fit the unfathomable onto a page or a screen, or into the limited confines of the human mind. These charts show tidy concentric rings, planets like pearls on a string, a cozy family of worlds orbiting a friendly central star. They present a universe that is knowable, navigable, perhaps even conquerable. But the truth is vastly different. The truth is wilder, more terrifying, and achingly immense. And understanding that immensity reveals a profound and difficult conclusion that this cosmic backyard we call home is also a cage. A beautiful, sprawling, intricate prison from which we may never escape. Our journey to understand this begins here, on the sunlit shores of a world teeming with life. Earth. From this vantage point, the cosmos feels accessible. We can look up and see our celestial companion, the Moon, 250,000 miles away, a distance we have crossed. It took our finest technology and bravest souls just a few days. A long weekend's journey in the grand scheme of things. It hangs in our sky, a testament to our ambition, the only other world on which a human foot has ever left its print. It whispers a seductive promise that the void is ours for the taking, that the planets are merely stepping stones on a path to the stars. Let us pull back and test that promise. We accelerate away from our blue marble, watching continents shrink and oceans merge into a single shimmering jewel. The Moon whips past us, its cratered face a familiar landmark. Now we race outward into the sunless territory between worlds. Our first planetary neighbor, Mars, beckons. The red world, the focus of so much of our hope and speculation. On our tidy maps, it looks like it's just next door, a short hop across the cosmic street. But even for our fastest robotic probes, this is no short hop. It is a voyage of 7, 8, even 9 months. A journey through a profound vacuum exposed to the fury of solar radiation. A human crew would spend years of their lives just for a round trip. And yet, from this new perspective, Mars is still incredibly close. We are still huddled right next to our parent star. The true scale of our solar system begins to reveal itself now. We push farther, crossing a vast, empty chasm. This is the main asteroid belt, a ghostly ring of rubble. The pulverized remains of a planet that never formed. Millions of rocks from pebbles to dwarf planets tumble in the dark. A treacherous yet surprisingly sparse cosmic minefield. We navigate its phantom lanes and emerge into a new domain, the realm of the giants. And here all our earthly sense of proportion is shattered. Here is Jupiter, a world so colossal it beggars belief. A failed star cloaked in storms. Its great red spot alone is a tempest wide enough to swallow our Earth whole. Jupiter is more than twice as massive as all the other planets combined. Its gravitational influence is immense, a stabilizing force and a cosmic shield protecting the inner worlds from a constant hail of comets. Its journey, time from Earth, not months but years. Our Juno probe took 5 years to reach its swirling cloud tops, 5 years to cross what looks like a handspan on our classroom charts. The distances are beginning to feel less like journeys and more like lifetimes. We continue outward, the sun shrinking behind us to a brilliant distant star. We glide past the majestic rings of Saturn, a breathtakingly delicate structure, a celestial work of art. A filigree of ice and dust, stretching for hundreds of thousands of miles, yet in some places only a few dozen feet thick. It's a world of impossible beauty, orbited by a bewildering collection of moons. From Titan with its methane seas to icy Enceladus hiding a subsurface ocean, to reach this place took our Cassini spacecraft nearly 7 years. 7 years of silent coasting through the void. 7 years to arrive at a world that is still incomprehensibly in our immediate cosmic neighborhood. The light from our sun, traveling at the ultimate speed limit of the universe, takes over an hour to reach these distant rings. When we look at Saturn from Earth, we are seeing it as it was an hour ago. The light is growing faint now. The cold is absolute. We press on into the deep twilight of the outer system. Here lie the ice giants Uranus and Neptune, ethereal blue-green orbs, mysterious and largely unexplored. Voyager 2, one of humanity's most audacious creations, gave us our only close-up glimpses of these remote worlds. It took Voyager 9 years to reach Uranus, and a staggering 12 years to fly past Neptune. 12 years. A child born on the day of its launch would be entering adolescence by the time the first images of Neptune's deep blue haze reached home. The sun from here is just a pinprick of intense light. Still the brightest star in the sky, but its warmth is gone. This is a place of profound, permanent cold. A place where orbits are measured not in years, but in human lifespans. Neptune takes 165 Earth years to circle the sun once. No human being has ever lived long enough to see it complete a single orbit. And here our familiar map ends. This is the solar system we were taught. The sun, 8 planets, a few belts of debris. A grand but perhaps ultimately comprehensible system. But this is where the lie of convenience unravels. This is where the true, soul-crushing scale of our home begins to dawn. Because what we have just traversed, this entire realm of the planets from Mercury out to the orbit of Neptune, is nothing. It is a tiny, warm, brightly lit patch at the very center of a colossal darkness. We have not even begun to see how big the solar system truly is. To find the real border, we must travel farther. We must journey beyond the farthest planet into a region of myth. Welcome to the Kuiper Belt. This is not a simple ring of asteroids like the one between Mars and Jupiter. This is a vast wraith-like disk, a cosmic attic filled with the leftovers of creation. It begins near Neptune's orbit, but it stretches outward for billions of miles. It is 20 times as wide and 100 times more massive than the asteroid belt. We are now in a place where the sunlight is 400 times fainter than on Earth. The darkness here is almost absolute, and it is teeming with unseen objects. Trillions of them. Icy bodies, frozen worlds, comets waiting for a gravitational nudge to begin their long fall toward the Sunday. This is the home of Pluto. For decades we called it our 9th planet, the lonely sentinel at the edge. We now understand it is no sentinel. It is a gatekeeper. It is simply the first and one of the largest of these Kuiper Belt objects that we happen to notice. Our New Horizons probe, the fastest machine ever launched from Earth, took nearly a decade to reach Pluto, traveling at over 36,000 miles per hour. A decade of flight to reach the beginning of this new dark frontier. Imagine that journey. 10 years in the black. And upon arriving, discovering that your destination is merely the first grain of sand on the shore of an ocean you had never conceived. This is the reality of the Kuiper Belt, a sprawling, ghostly expanse that dwarfs the planetary region. We are now so far from home that a radio signal moving at the speed of light takes more than 5 hours to reach us, a 5-hour delay in communication. This is no longer a journey, it is an exercise in isolation, a voyage into a realm where the familiar laws of time and distance break down. And still we are not at the edge. We have not found the wall. We are not even close. To find the true boundary of the sun's dominion, we must understand what a solar system fundamentally is. It is not just a collection of objects held by gravity. It is a kingdom defined by the influence of its star. Our sun does not just radiate light and heat. It breathes. It exhales a constant supersonic stream of charged particles. A stellar wind that flows outward in all directions at 1,000,000 miles per hour. This is the solar wind. And it carves out a gigantic bubble in the interstellar medium, a protective sphere of influence around our star and its planets. This bubble is called the heliosphere. And everything we have seen so far, Earth, Jupiter, the Kuiper Belt, is nestled deep, deep inside this bubble. It is our shield. It deflects the deadly cosmic rays that pervade the galaxy, allowing life to flourish on our world. We live and die inside this magnetic cocoon, utterly dependent on its invisible protection. For 40 years, two remarkable emissaries have been traveling towards its edge, the Voyager 1 and Voyager 2 spacecraft. Launched in the 1,970 seconds, they are humanity's farthest creations, lonely pilgrims on an epical journey into the unknown. For decades, they flew through the familiar territory of the solar wind. Then something changed. In 2012, after 35 years of flight, Voyager 1 detected a sudden dramatic shift. The solar wind particles that had buffeted it for its entire life vanished. Simultaneously, the probe was struck by a powerful blast of cosmic rays from the galaxy beyond. The environment had transformed completely. The temperature plummeted. The magnetic field changed direction. The scientists at Mission Control were stunned. After years of anticipation, the moment had arrived. Voyager 1 had crossed the heliopause. It had punched through the outer boundary of the Sun's bubble. It was the first human-made object to enter interstellar space. Voyager 2 followed it 6 years later, crossing at a different point. They are our scouts, our silent witnesses in the great ocean between the stars. Think about what this means for our understanding of scale. It took a machine traveling 17 times faster than a speeding bullet more than 35 years to leave the Sun's direct atmospheric influence. 35 years to exit the bubble. If the distance from the Earth to the Sun were the length of a football field, the planetary region would end around the 50-yard line. The heliopause, the edge of this bubble, would be over 2 miles away. This is the kingdom we inhabit. A vast, sprawling territory defined by the breath of our star. A domain so large it requires decades of travel at incredible speeds just to cross. Surely this must be the edge. This must be the final border of our solar system, but it is not. The most staggering, the most incomprehensible, the most definitive boundary lies unimaginably farther out. A structure so vast and so ethereal that for most of history we did not even know it existed. Its discovery has forever changed our place in the universe. It is the true scale of our cosmic prison. Beyond the heliopause, in the deep interstellar darkness, the Sun's gravitational hold persists. Its light may be feeble, its solar wind extinguished, but its gravity, the fundamental force of its mass, reaches on and on. And out here, in the cold, dark abyss, it holds sway over one last colossal realm. We have never seen it directly. We may never see it. We know it exists only by the ghostly messengers it sends us, comets. For centuries we watched them blaze across our skies, their origins a complete mystery. We now know they come from this place, a theoretical yet necessary structure called the Oort Cloud. It is not a belt, it is not a disk, it is a shell, a gigantic spherical shell of icy bodies that completely encases our solar system. Imagine our Sun and all its planets as a single grain of sand. The Oort Cloud would be a sphere of cosmic debris surrounding that grain, a sphere over a mile wide. The numbers are difficult to process. It is believed to contain not billions, but trillions of objects. Frozen remnants from the birth of our solar system flung out to the farthest possible orbit by the gravity of the young giant planets. They drift in a slow cosmic ballet barely held by the Sun's fading grip. This is the Sun's true gravitational frontier. This is the Great Wall of the solar system, and its distance from us is the most profound number you will ever hear. We measure the inner system in light minutes and light hours. It takes sunlight 8 minutes to reach Earth, about 5.5 hours to reach Pluto. We measure the galaxy in light years. A light year is the distance light travels in 1 year, nearly 6 trillion miles. The nearest star to our Sun, Proxima Centauri, is a little over 4 light-years away. The Oort Cloud begins at a distance of perhaps 2,000 times the Earth-Sun distance. But it doesn't end there. It extends outwards to 50,000, 100,000, perhaps even 200,000 times the distance from the Earth to the Sunday. Its outer edge may reach more than 3 light-years from home. It may stretch more than halfway to the next star. Think about that. Our solar system, our home, this collection of worlds orbiting our Sun, is a structure so immense that it extends more than halfway to Alpha Centauri. Voyager 1, traveling for over 40 years at tens of thousands of miles per hour, is now about 17 light-hours away from us. At its current speed, it will take another 300 years just to reach the inner edge of the Oort Cloud, and it would take it 30,000 years to cross to the other side. 30,000 years. Human civilization from the first cave paintings to the present day is only about 30,000 years old. One of our fastest machines would need an entire span of human history just to traverse the solar system's outermost layer. This is the truth concealed by our tidy maps. This is the reality of our cosmic backyard. It is not a small collection of planets in a manageable space. It is a colossal, multi-layered structure of almost inconceivable size, a tiny sun-drenched core where life exists, surrounded by a vast, dark disk of frozen worlds, all of it encased in a protective magnetic bubble, and that entire construct is surrounded by an almost mythical trillion-strong shell of comets stretching for light-years in every direction. This is our home. And this is our confinement. When we speak of leaving the solar system, we are not speaking of a trip to Mars. We are not speaking of a mission to the moons of Jupiter. We are not even speaking of a voyage to the Kuiper Belt. We are speaking of crossing a gulf that would take our best technology tens of thousands of years to navigate. We are speaking of a journey so long it ceases to have any human meaning. The challenge is not one of engineering. It is a challenge of physics and time. The speed of light, the ultimate cosmic speed limit, appears to be absolute. The energy required to approach that speed is astronomical, and the distances involved mock our ambitions. Even if we could build a ship that traveled at 1/10 the speed of light, a feat far beyond any conceivable technology, today, it would still take over 30 years to pass the outer edge of our own solar system. 30 years just to get out of our own backyard and into the true void between stars, and decades more to reach even the very nearest one. This is the tyranny of distance. It is the fundamental rule of our universe. Space is big, unimaginably big, and we are a young species born on a small world, nestled in the very heart of a system far larger than we ever dreamed. We have spent a century taking our first faltering steps into this immensity. But as we look out past the familiar planets and into the great darkness beyond, the true nature of our challenge becomes clear. The question is no longer just how we explore our solar system. The question is whether, in any meaningful sense, we can ever truly leave it. Are we destined to forever be children of the sunbound, by its gravity shielded by its winds and forever trapped within the distant walls of its icy silent kingdom? The maps have lied to us, and the truth they concealed is the greatest challenge humanity will ever face. Look up tonight into the deep velvet blackness. What you perceive is an illusion, a beautiful lie handed down to us by the wiring of our own minds. You see a dome, a celestial ceiling pricked with light. It feels close, intimate, a canopy draped over our world. This feeling is an echo of our species' first great thought, our first attempt to sketch the architecture of reality. For nearly all of human history, this was not a feeling. It was the unquestioned truth. Our story of the solar system's size begins not with a measurement, but with a profound and comforting mistake. We believed we lived at the very center of existence. The Earth was the unmoving stage for the cosmic drama, and everything, absolutely everything, revolved around us. The sun, our life-giving star, made a daily pilgrimage across our sky. The moon, a loyal companion, traced its silvery path around our world. And the stars were not distant suns, but tiny, perfect lights, perhaps divine fires fixed to a solid crystalline sphere that rotated with majestic, predictable grace. This universe was not empty or cold, it was full. It was a set of nested spheres, a divine piece of clockwork with Earth as its precious, protected heart. The scale of this cosmos was knowable, human-sized. The edge of everything was just beyond the most distant lights. Our solar system was in fact the entire universe. There was no beyond. There was only the celestial sphere and then the mind of God. It was a model born of elegance, philosophy, and faith, and for a time it worked. But there was a problem. A subtle, nagging imperfection. Among the fixed and orderly stars there were wanderers, 5 brilliant points of light that refused to obey the rules. Mercury, Venus, Mars, Jupiter, and Saturn. The Greeks called them planetes, the wanderers. They drifted against the stellar backdrop with a maddening independence. They would slow down, stop, and even move backward for a time in a baffling celestial dance known as retrograde motion. This was cosmic anarchy. It was a flaw in the perfect machine. How could you explain this bizarre behavior if everything moved in perfect circles around the Earth? For centuries, the greatest minds on the planet wrestled with this puzzle. Their solution was a testament to human ingenuity, a breathtaking attempt to salvage a cherished idea. They imagined a mechanism of staggering complexity, a universe of wheels turning upon other wheels. The planets they proposed did not orbit the Earth directly. Instead, they moved in a small circle, an epicycle, while the center of that circle traced a larger path around us. It was a clockwork of sublime intricacy, a web of celestial gears designed to force the heavens into obeying our assumptions. With enough epicycles, you could explain away any anomaly. You could make the cosmos dance to any tune you wished. This system, refined by the great astronomer Ptolemy, became doctrine for over 1400 years. It was a magnificent, intricate, and profoundly wrong description of reality. It preserved our central place, but it kept the universe small, a cozy theatre built just for us. Our home wasn't a planet, it was the foundation of everything. But a new idea was stirring, a quiet, dangerous thought that would ultimately shatter the crystal spheres forever. It came from a Polish astronomer named Nicolaus Copernicus. He looked at the convoluted system of epicycles, this cosmic machinery of spiraling complexity, and he proposed a solution of daring and terrifying simplicity. What if the dance of the planets seemed so complex, not because their paths were strange, but because our viewpoint was? What if the Earth was not the center of the dance at all? What if it was just one of the dancers? His revolutionary model placed the sun at the heart of the cosmos. The Earth was demoted, cast out from its privileged throne, and sent spinning into orbit, just another world, another wanderer. Suddenly, the bizarre retrograde motion of Mars made perfect sense. It was an illusion created as our own faster-moving Earth overtook the red planet on an inside track like one runner lapping another. The maddening complexity dissolved into beautiful, simple harmony. The epicycles, the wheels on wheels, were no longer needed. The heavens snapped into focus with a new, clean logic. But this revelation came at a staggering cost to our sense of self. To accept it, you had to believe that the ground beneath your feet was hurtling through the void at an unimaginable speed. You had to accept that our world was not special. It was a psychological earthquake. For decades, the Copernican idea was deemed absurd, a mathematical fantasy. It defied common sense, it contradicted scripture, and it felt profoundly, viscerally wrong. The universe we knew, the one built around us, was a difficult thing to let go. The truth often is, the final verdict would not be delivered by mathematics alone. It would arrive through a new invention, a spyglass. that a man named Galileo Galilei would turn toward the heavens. His simple telescope was a weapon aimed at the heart of the old world, and what it revealed would tear down the last pillars of the geocentric cosmos. He looked at the moon and saw not a perfect ethereal orb, but a world scarred with mountains and valleys, craters and plains. It was a place as real and imperfect as the earth itself. The heavens, it seemed, were not made of some divine, flawless substance. He turned his lens toward Venus and watched as it went through phases just like our moon, from a slender crescent to a brilliant full disk. This was impossible in Ptolemy's system. It was the celestial equivalent of a signed confession, irrefutable proof that Venus orbited the Sun, not the Earth. But his most devastating discovery, the true revolution, came when he observed the planet Jupiter. He saw it not as a single point of light, but as a tiny disk flanked by 4 small faint stars that seemed to follow it. Night after night he watched them, his heart pounding. They were not stars. They were moons, a family of worlds locked in orbit around the giant planet. Here in the eyepiece of his telescope was a miniature solar system, a clear, undeniable demonstration that not everything in the universe revolved around the Earth. The case was closed. The 1400-year-old worldview was shattered. The Earth was moving. The Sun was the center. And with that realization, the universe exploded in size. The stars, once lights on a nearby ceiling, were now revealed for what they truly were: unimaginably distant suns, each potentially with its own family of worlds. The space between the planets, once just a short distance in a set of nested spheres, became a chasm of terrifying emptiness. The comfortable human-scale cosmos was gone forever. In its place was a vast, silent, and profound abyss. Our solar system was no longer the entire universe. It was a tiny, sun-drenched island in an infinite cosmic ocean. We were adrift, and we had a new map. For the next century and a half, this new map seemed complete. 6 planets, including our own, circling a single star: Mercury, Venus, Earth, Mars, Jupiter, and the majestic ringed Saturn. Saturn was the sentinel, the magnificent guardian at the final frontier. Beyond its icy rings there was thought to be nothing, just the endless star-dusted darkness. The known solar system ended at Saturn. This was our home, redrawn and expanded, but now fully charted. The age of discovery, it seemed, was over. Or so we thought. The next great leap in our cosmic awareness would not come from a renowned professor at a grand observatory. It would come from a musician in Bath, England, a man with an insatiable, obsessive curiosity for the night sky. His name was William Herschel. He was not content with the instruments of his day. He wanted to see deeper, farther, with more clarity than anyone before. So he taught himself the arduous art of grinding mirrors and building telescopes, crafting instruments of unprecedented size and power in his own home. Night after night, year after year, he undertook a Herculean task to systematically survey the entire northern sky, to examine and catalogue every single object he could see. It was a painstaking, relentless search for anything. He wasn't hunting for a planet. No one was. The solar system was considered a closed book, its members already counted. Then on the 13th of March, 1781, while sweeping through the constellation of Gemini, Herschel paused. He saw something that wasn't on his star charts. It wasn't a sharp, singular point of light like a star. It appeared as a small, faint, greenish disk. He had seen thousands of stars, but this was different. It had a tangible shape, a visible body. His first thought was that he had found a new comet, a hazy visitor from the solar system's distant fringe. He tracked it for several nights, his excitement growing. The strange object was moving. It was definitely a member of our solar family. But as he and other astronomers plotted its course, the mystery deepened. It didn't behave like a comet. Its orbit was slow, majestic, and nearly circular. Comets travel in highly eccentric, elongated paths, swooping in close to the Sun and then flinging back out. This object's journey was far too stately, too planetary. The calculations poured in from across Europe, each one pointing to the same astounding conclusion. This was not a comet, it was a world. It was a seventh planet, orbiting the Sun at a staggering distance far beyond the sentinel Saturn. The discovery was an absolute thunderclap in the scientific world. It was the first planet to be discovered since antiquity, the first to be found with a telescope by a deliberate search of the sky, and its existence completely redrew the map of our cosmic home once again. With this single faint point of light, the known diameter of the solar system doubled. In an instant, the boundary of our neighborhood was pushed out into a realm of cold and darkness previously unimaginable. Saturn, the old distant king, was now just a midway point. The frontier had been obliterated and re-established twice as far away as anyone had ever dared to dream. The planet was eventually named Uranus after the Greek god of the sky. Its discovery was more than just a new entry in a catalogue. It was a profound lesson. It taught us that the solar system was not a finished story, that there were still secrets hidden in the darkness, that our map was still incomplete, and it raised a tantalizing question: if we missed one world, could there be others? The discovery of Uranus was a triumph of observation. The discovery of the next world would be something else entirely. It would be a triumph of pure reason, a story of a planet hunted not with a telescope, but with the tip of a pen. It all began with a nagging problem, a cosmic anomaly. Uranus was misbehaving. As astronomers tracked the new planet through the decades, they found that it refused to follow its predicted path. Its orbit was wrong. The deviation was tiny, a minuscule wobble in its majestic course. But in the precise world of celestial mechanics, it was a scandal. Isaac Newton's laws of universal gravitation were the bedrock of physics. They were supposed to be perfect, immutable. They had predicted the paths of comets and the tides of oceans, but they could not fully account for the errant wandering of Uranus. The planet would drift ahead of its schedule, then inexplicably fall behind. It was as if some unseen force, a ghostly hand, was gently tugging it, pulling it away from its ordained trajectory. This discrepancy sparked one of the great scientific debates of the 19th century. Had we finally found the limits of Newton's laws? Did gravity itself behave differently in the cold, dark frontiers of space? Or was there another explanation? A few brilliant minds began to contemplate a radical possibility. What if Newton's laws were not the problem? What if there was something else out there, a hidden variable, perhaps an eighth planet unknown and unseen, was orbiting even farther out in the abyss? Its faint but persistent gravitational pull could be the culprit, the phantom force tormenting Uranus's orbit. To search for such a world with a telescope would be hopeless. It would be like finding a single specific grain of sand on an endless beach. The only way to find it was to predict its location, to use the wobble of Uranus as a clue, a gravitational breadcrumb leading to the hiding place of the unseen world. It was a mathematical challenge of almost inconceivable difficulty. You had to work the problem backward. From the tiny gravitational disturbance, you had to deduce the mass, the orbit, and the current position of a massive, invisible object millions of miles away. Two men, unaware of each other's work, took up this monumental challenge. In England, a young, brilliant Cambridge mathematician named John Couch Adams. In France, the established and formidable astronomer Urbain Le Verrier. For years, they toiled in intellectual solitude, filling page after page with labyrinthine calculations. It was an abstract hunt, a search conducted in the realm of pure thought. They were attempting to conjure a world into existence from the ghost of its own gravity. Both men, through sheer force of intellect, arrived at a prediction. They calculated where in the zodiac this phantom planet ought to be. Leverrier, confident in his figures, wrote to the Berlin Observatory. He implored the astronomers there to point their telescope at a specific location in the constellation of Aquarius. He told them they would find a new planet. It was an act of extraordinary intellectual arrogance or genius. The head of the observatory, Johann Galle, was skeptical, but the request from the great Leverrier could not be ignored. On the night of September 23rd, 1846, Galle and his assistant aimed their telescope at the designated coordinates. They began to meticulously compare the stars they saw with the patterns on their detailed star charts. For less than an hour they scanned the field of view. Then a cry of astonishment. Galle saw a point of light that was not on the map. It was a tiny 8th magnitude star, precisely where Leverrier had said it would be. They watched it. It was moving. The ghost was real. They had found it. The world was named Neptune, after the Roman god of the sea. Its discovery was perhaps the most profound moment in the history of science. Humanity had not stumbled upon this world. We had summoned it. We had reached out into the void with the power of mathematics and pinpointed the existence of a new planet. It was the ultimate validation of Newton's laws and a staggering demonstration of the power of the human mind. And once again, the solar system had doubled in size. The frontier, which had been at Saturn, then at Uranus, was now pushed out to the orbit of this new blue frozen giant. Our conception of home had expanded in a way that would have been utterly inconceivable to our ancestors just a few generations before. We had journeyed in thought and observation from a tiny enclosed world at the center of a celestial sphere to a magnificent system of 8 planets orbiting a star, a system stretching across billions of miles of empty space. Each discovery was a humbling revelation, a forceful reminder that our knowledge was incomplete, our assumptions fragile. From the wanderers that broke the perfection of the ancient sky to the telescope that shattered the Earth's central throne, from the musician who stumbled upon a new kingdom of ice and darkness to the mathematicians who found a world with numbers alone, our understanding had been forged in a series of intellectual revolutions, each one pushing the perceived edge of our domain further and further into the black. By the dawn of the 20th century, we had a new map, 8 worlds, a family portrait with distant Neptune as the final lonely outpost. Surely now, we thought, surely now we have found the edge. Have we finally measured the true scope of our solar shores? Or is the darkness beyond Neptune hiding even bigger secrets? Everything you think you know about the solar system's edge is wrong. You have been living inside a ghost, a colossal, invisible structure that is the only reason life on Earth exists at all. It is the single largest object the sun has ever created, and yet you will never see it, never touch it, never feel it. This is the heliosphere, and it is our first line of defense in a universe that is not empty but actively hostile to the very chemistry of life. To understand this phantom kingdom, you must first reimagine the Sunday. It is not merely a quiet, distant ball of light. It is a ferocious, churning engine of thermonuclear fusion, and from its superheated outer atmosphere, the corona, it unleashes a constant, ferocious storm into the cosmos. We call it the solar wind, but the name is a gentle deception. This is no terrestrial breeze. This is a tempest of charged particles, a plasma river of protons and electrons perpetually erupting from our star. It streams outwards in every direction, 1,000,000 miles an hour, a relentless gale that scours the surfaces of worlds. It is this wind that gives comets their magnificent tails, stripping away their dust and ice into ethereal banners. For billions of miles, this solar hurricane travels a torrent of the sun's own substance, filling the space between the planets. It carves out a bubble, a vast magnetic cocoon inside the galaxy. This sphere of influence, this solar dominion, is the heliosphere. Inside it, we are in the sun's territory. Everything is bathed in its light, warmed by its heat, and shielded by its ever-expanding magnetic field. This is the harbor in which Earth sails. But a harbor only has meaning if there is a storm outside. Beyond this bubble lies the true void, interstellar space. It is a realm of profound, cold, and unimaginable antiquity. A thin, tenuous medium filled with the dust and gas of long-dead stars, the raw material for new suns and worlds yet to be born. But it is not a peaceful realm. It is saturated with a lethal rain of cosmic rays. These are the atomic nuclei of shattered stars, remnants of ancient cataclysmic supernova explosions. They are accelerated to nearly the speed of light by galactic magnetic fields shredding through space like microscopic bullets. If Earth were exposed directly to this unceasing bombardment, our atmosphere would be stripped away. The very code of life DNA would be fractured and corrupted. The cosmos in its raw state is a sterilizing agent. Our heliosphere is the shield that stands against this onslaught. At its farthest frontier, a battle of cosmic proportions is being fought. The sun's outward flowing wind, now billions of miles from its source, begins to thin, to weaken, to lose its momentum. It is slamming into the wall of the interstellar medium, the collective pressure of all the galaxy's winds pushing back. This colossal confrontation creates a series of boundaries, invisible lines drawn in the fabric of space. The first is called the termination shock. Imagine a supersonic jet's sonic boom frozen in time and space. Here, the solar wind, after its journey across the entire planetary system, abruptly slows from 1,000,000 miles per hour to a mere 250,000. It is a shockwave of staggering proportions, a turbulent, chaotic frontier where our sun's breath is forced to a subsonic whisper. It is a boundary we never even knew existed until we sent emissaries, our silent, tireless explorers. In the late summer of 1977, two spacecraft left our world, Voyager 1 and Voyager 2. They were built to last 5 years to give us our first fleeting glimpses of Jupiter and Saturn. They were triumphs of engineering, but no one truly dreamed of the epic journey that lay ahead of them. Decade after decade, they sailed on their power, fading their instruments, aging, but their senses still sharp. They became humanity's most distant creations, our first true interstellar scouts. They were traveling towards the great ghost, the heliosphere's edge. They were going to touch the void. For years, scientists on Earth watched their data with bated breath. The Voyagers were flying blind into a region we had only theorized about. What would the end of the Sun's kingdom feel like? In 2004, Voyager 1 sent back the first clue. Its instruments registered a sudden, dramatic spike in magnetic field strength. The flow of particles around it grew turbulent, chaotic. It had crossed the termination shock. It had entered the final strange realm of our solar system, a region called the heliosheath. Here, the solar wind is no longer a directed gale. It is a roiling, frothing sea of plasma pressed and squeezed by the interstellar forces waiting just beyond. Voyager 1 spent another 8 years traversing this bizarre zone. Then, in the summer of 2012, something changed, something profound. The data streaming back to Earth from nearly 12 billion miles away painted an unmistakable picture. The constant hiss of solar wind particles bombarding the craft ceased. It fell silent. In its place, a new sound emerged in the data. A sudden screaming surge of high-energy galactic cosmic rays. The craft's particle detectors were overwhelmed. The concentration of particles from outside our solar system jumped by a factor of nearly 100. The magnetic field, once aligned with the Sun, suddenly twisted, realigning itself with the galaxy at large. The conclusion was breathtaking. Voyager 1 had crossed the heliopause. It had punched through the gossamer wall of our solar bubble. It was the first human-made object to enter interstellar space. Headlines around the world screamed a simple, triumphant message: Voyager leaves the solar system. It was a glorious, heroic, and almost completely inaccurate statement. Leaving the sun's magnetic cocoon is not the same as leaving its grip. The heliosphere, for all its colossal size, is just the inner sanctum. The true scale of our star's dominion is written not by the wind, but by the oldest, most patient, and most fundamental force in the universe: gravity. The sun's gravitational empire extends far, far beyond the reach of its wind. It stretches into the darkness 1,000 times farther than Pluto. It envelops a realm so vast, so empty, and so cold that it almost defies description. This is the true solar system, and its final border is a place of mythic proportions, the Oort Cloud. You cannot see this place. No telescope will ever resolve it. It is less a structure and more a breathtaking concept, a ghost haunting the periphery of our star's influence. Its existence was first theorized by the Dutch astronomer Jan Oort in 1950. He was wrestling with a cosmic mystery, the long-period comets. These are not the regular visitors like Halley's Comet, which return every few decades from the Kuiper Belt beyond Neptune. These are celestial apparitions, comets like Hale-Bopp or Hyakutake, which fall into the inner solar system on orbits lasting millions of years. They are pristine ancient relics, and they seem to come from nowhere and everywhere. They don't arrive on the same plane as the planets. They plunge in from above, from below, from every conceivable angle. Oort reasoned that if these comets were coming from all directions, their source must be a sphere, a gigantic spherical shell of icy bodies completely surrounding our solar system, a cosmic reservoir of frozen worlds held in a delicate gravitational dance at the very edge of the sun's command. This was a staggering intellectual leap. He was postulating a component of our solar system so enormous it would dwarf everything we knew, and all the evidence since has proven him right. The Oort Cloud is the solar system's deep freeze attic. It is a celestial graveyard containing the leftover rubble from the formation of the planets 4.5 billion years ago. Trillions of objects ranging in size from mountains to small worlds composed of water, ice, methane, ammonia, and rock. They are the primordial building blocks of our home, flung out into the abyss by the gravitational chaos of the giant planets in the solar system's youth. And there they have remained suspended in an unimaginable cold, drifting in a darkness the sun's light can barely touch. To speak of its scale is to risk madness. We measure the inner solar system in astronomical units. 1 AU is the distance from the Earth to the Sun, 93 million miles. Pluto orbits at around 40 AU. The Voyager probes, after nearly half a century of travel, are now just over 160 AU from home. The Oort Cloud doesn't even begin for another 1,000 AU. Its main body is thought to lie between 20,000 and 50,000 astronomical units away from the Sun. Its outermost edge might extend to 100,000 AU, or even 200,000. Let's try to grasp that. 100,000 AU is more than just a big number. It is 1.6 light years. It means the Sun's gravitational kingdom, our solar system, stretches nearly halfway to the next nearest star, Proxima Centauri. It means that light, the fastest thing in the universe, takes more than 1.5 years to travel from the Sun to the outermost subjects of its gravitational rule. Think about Voyager 1, our fastest and farthest messenger. It travels at 35,000 miles per hour, a blistering 17 kilometers every second. At that speed, it would take Voyager 300 years just to reach the inner edge of the Oort Cloud. To cross it completely would require more than 30,000 years, 30 millennia of flight through a near-perfect vacuum. This is why leaving the heliosphere is not leaving the solar system. It is like stepping off your front porch and claiming you've emigrated. Voyager 1 has only just begun its journey into our star's true territory. It is a territory of almost perfect emptiness. Though there may be trillions of objects in this great cloud, the space between them is impossibly vast. Each icy nucleus is separated from its nearest neighbor by tens of millions of miles. An astronaut floating in the heart of the Oort Cloud would see nothing. Absolute unending blackness in every direction. The sun would be just the brightest star in the sky, indistinguishable from any other, offering no discernible warmth. You would feel a gravitational pull so faint, so tenuous, it would be utterly imperceptible. Yet that pull would be just strong enough to keep you bound to the sun, stronger than the faint siren call of any other star in the galaxy. You would be in the sun's domain. You would be home. And this is not a static, dead museum of cosmic artifacts. The Oort Cloud is a dynamic frontier. Out here on the ragged edge of the sun's influence, other forces come into play. The gentle gravitational pull of a passing star millions of years from now can stir this celestial beehive. The tidal forces of the Milky Way galaxy itself, the collective gravity of 400 billion stars, can ripple through the cloud. These subtle nudges are enough. They can disturb the eons-long orbit of a single icy body. A tiny perturbation, a gravitational whisper, is all it takes to send one of these sleeping worlds on a new trajectory. A long, slow, million-year fall towards the distant bright star in its sky, towards the Sunday. As it falls inward past the orbits of Neptune and Jupiter, the sun's warmth begins to work on its frozen surface. The ancient ices begin to sublimate, turning directly into gas. Dust trapped for billions of years is released. A magnificent coma, a glowing atmosphere begins to form. The solar wind catches this new material, pushing it out into the twin tails that make these visitors so unforgettable. An object that spent its entire existence in darkness and silence is transformed into a spectacular comet, a breathtaking spectacle for a new transient species on the third planet. We look up in wonder, witnessing the arrival of a messenger from the true deep of our own solar system, a place we will almost certainly never visit. This, then, is the staggering reality of our cosmic address. Our home is not a small collection of 8 planets and a few belts of asteroids. Our home is a bubble of warm, life-giving wind encased within a ghostly spherical empire of ice a light-year across. A domain so vast that our fastest machines are but snails crawling across it. A gravitational prison from which we have no practical means of escape. The very concept of leaving the solar system is a fantasy, a dream for a civilization that has not yet come to terms with the profound, soul-crushing scale of its own backyard. We have sent our probes beyond the fire into the cold, but they have not yet escaped the darkness that belongs to us. And for humanity, the journey has not even begun. We have journeyed far. We have pushed past the rocky inner worlds and crossed the great chasm of the asteroid belt. We have sailed by the gas giants, those colossal swirling kingdoms that hold court in the middle darkness of our solar system. We have even watched the distant sun shrink to a brilliant star, a guiding light in a sea of ever-deepening blackness. But we have not yet left home, not even close. Out here, beyond the orbit of the last known planet Neptune, beyond the scattered frozen relics of the Kuiper Belt, we face the true soul-crushing scale of our cosmic isolation. We stand at the shore of an ocean whose size defies intuition. Its name is the Oort Cloud, and it is the Great Wall at the end of our solar system. This is not a place of light and spectacle. It is a ghostly sphere of trillions of ice and rock comets, each one a frozen time capsule from the birth of our Sunday. They are loosely bound, barely tethered by the sun's fading gravity. This immense spectral shell surrounds us completely. To leave the sun's domain, you must cross it. There is no other way. So let us imagine we wish to undertake this monumental voyage. Let us pretend we are commissioning the greatest journey in human history. We need a ship, not a vessel of science fiction, but of fact. We must select the fastest object humanity has ever forged. That champion of velocity is the Parker Solar Probe. It is a masterpiece of engineering designed for a hellish mission to fly through the atmosphere of our own star. To achieve this, it executes a series of daring gravitational maneuvers, using the immense pull of Venus to slingshot itself closer to the Sunday. With each pass, it steals orbital energy and accelerates. It whips around our star riding a gravitational wave. At its peak, Parker reaches speeds that are difficult to comprehend. Over 700,000 kilometers per hour. Nearly 200 kilometers every single second. You could travel from London to New York in less than 30 seconds. You could circumnavigate the entire Earth in just over 3 minutes. This is the pinnacle of our propulsive capability, our best effort. Now let us point this magnificent dart, this sliver of human ambition, not toward the sun but away from it into the great unknown. Let's give it that maximum sun-assisted velocity and send it outward. Its target the inner edge of the Oort Cloud, the very beginning of the end of our solar system. How far must it travel? The distances are now so vast that our familiar units begin to fail us. Kilometers and miles are like counting grains of sand on a beach. So astronomers use a different yardstick, the astronomical unit, or AU. 1 AU is the average distance from the Earth to the Sunday, about 150 million kilometers. The inner boundary of the Oort Cloud is believed to begin at roughly 2,000 astronomical units away from our Sunday, 2,000 times the distance from Earth to our star. It is a chasm of almost unimaginable emptiness. So we have our speed, our staggering record-shattering velocity, and we have our destination, a seemingly arbitrary line in the void. The calculation is simple. The result is shattering. To cross that gulf of 2,000 AU, our fastest spacecraft traveling at a speed that could circle our planet in minutes would need more than 3,000 years, 3 millennia, just to reach the doorstep of the sun's most distant territory. Let that number sink in. 3,000 years ago, the Iron Age was just beginning in Europe. The city of Troy from Homer's epic was a recent memory. Great pharaohs ruled a vibrant Egyptian empire. The entire recorded history of Western civilization, the rise and fall of Greece, the Roman Empire, the Middle Ages, the Renaissance, the Industrial Revolution, the Space Age, all of it would unfold from start to finish, and our probe would still be voyaging through the silent, empty darkness. It would be a ghost ship, an artifact of a long-dead generation sailing on through a night with no end. And the most sobering part of this revelation, it would have only just arrived. The journey has barely begun, because the Oort Cloud is not a thin shell, it is a presence, it is an incomprehensibly vast and diffuse sphere. From its inner edge at 2,000 AU, it is thought to extend outward to 50,000 AU, perhaps even 100,000 AU. It is a cosmic no man's land of staggering proportions. To truly leave the solar system, you must cross all of it. Let's rerun our calculation for the onward journey. From that 3,000-year mark at the inner boundary, our tiny probe pushes ever outward deeper into the cometary halo. The sun is now just the brightest star in a sea of stars, its warmth non-existent, its light a distant piercing beacon. The probe travels through a realm where comets drift kilometers apart, a silent, stately dance in the near absolute zero of deep space. To traverse the main body of this cloud, to finally break free from the last lingering tendril of our sun's gravitational embrace, would take our Parker Solar Probe an additional 50,000 years, perhaps even longer. Let us be conservative and say a total journey of 60,000 years, 60 millennia. 60,000 years ago, our species, Homo sapiens, was just beginning its great migration out of Africa. Our ancestors were Stone Age hunter-gatherers, living in a world dominated by mammoths, cave bears, and Neanderthals. The very concepts of farming, of cities, of writing were tens of thousands of years in the future. The entire story of human civilization is but a footnote to the duration of this single outbound voyage. A message sent back from the probe as it finally exited the Oort Cloud would be arriving at a planet inhabited by a species that might be biologically, culturally, and technologically unrecognizable from the one that launched it. We would be sending a message to a future we cannot possibly imagine. This is the brutal, humbling arithmetic of our own cosmic backyard. We are prisoners of a scale we have yet to truly internalize. But the ambition of our species has never been confined to its own home. We look up at the night sky and we see other lights, other suns. We yearn to know what lies beyond our shores. So let us now set our sights on the ultimate prize. Let us attempt the first true interstellar journey. Our destination, the very nearest star to our own Sunday. It has a name that sounds deceptively close, like a neighbor. Proxima Centauri. It is a small, dim red dwarf star, part of the Alpha Centauri system. It is our closest cosmic port of call. If we could travel to any star, this would be the one. It lies just 4.2 light-years from Earth. A light year, the very term, is a piece of cosmic poetry. It is the distance that a beam of light, the fastest thing in the universe, travels in a single year. Light moves at a blistering 300,000 kilometers per second. It is a speed so absolute it forms the physical speed limit of reality. Nothing with mass can ever reach it. To speak of a light year is to speak of a gulf beyond human experience. 1 light year is nearly 9.5 trillion kilometers. Our destination, Proxima Centauri, is 4.2 times that distance, roughly 40 trillion kilometers away. Writing that number down doesn't do it justice. It is a stack of zeros that represents a fundamental barrier, a declaration from the universe itself, this far and no farther. But we are a species of voyagers. We must try. So once again we turn to our champion of speed, the Parker Solar Probe, a vessel forged in the fires of our star. We imagine it on a perfect trajectory, flung out of the solar system with all the velocity it can muster. Its mission to cross the unimaginable abyss to Proxima Centauri. How long would this epic odyssey take? We set our clocks. The probe screams past the orbit of Pluto. Decades pass. It enters the Kuiper Belt. Centuries turn to millennia. It breaches the inner Oort Cloud. The pyramids of Giza are built, crumble to dust, and are rebuilt by time. Our vessel sails on. Tens of thousands of years elapse. It finally exits the sun's domain. Now it is truly in interstellar space, the lonely void between suns. The darkness here is of a different quality. It is absolute. The sun has faded into the stellar tapestry, one light among many. The destination, Proxima Centauri, remains an unremarkable point of light, seemingly no closer than when the journey began. For thousands upon thousands of years, the view would barely change. The probe is a grain of sand crossing an infinite desert. The math is as simple as it is horrifying. 40 trillion kilometers divided by 700,000 kilometers per hour. The hours turn into days, the days into years, the years into centuries, the centuries into millennia. The final number arrives, not as a solution but as a judgment. 81,000 years. 81,000 years of travel through the cold and the dark to reach the very next star. Think of what this means. 81,000 years ago, our world was in the depths of an ice age. Vast glaciers covered much of North America and Europe. Humanity was not a planetary civilization, but a scattered collection of nomadic tribes struggling for survival against a hostile climate. Our species was a fragile experiment, its future utterly uncertain. If we launched that probe today, it would arrive at Proxima Centauri in a future so distant it renders our present moment insignificant. Generations would rise and fall like waves on the ocean. Languages would be born, evolve, and die. Entire civilizations could emerge, flourish for millennia, and vanish into history, and our tiny emissary would still be less than halfway to its destination. The craft itself would be an ancient derelict upon arrival. Its systems, however robust, would have long since failed. Millennia of bombardment by high-energy cosmic rays would have fried its electronics and degraded its materials. It would tumble into the Proxima Centauri system not as a messenger but as a silent, eroded piece of space debris, an anonymous relic from a forgotten people from a forgotten time. This is the sobering truth at the heart of our cosmic aspirations. We speak of interstellar empires and galactic federations. We dream of starships warping through space, of hopping from system to system, as if they were islands in an archipelago. But the physics of our reality presents us with a different story, a story of profound and inescapable isolation. The universe does not forbid these journeys. It simply makes them so long, so arduous, so far beyond the scale of a human life or even the life of a civilization that they become functionally impossible. The energy required to accelerate a meaningful payload to even a fraction of the speed of light is astronomical, dwarfing the entire energy output of our current global civilization. And even if we could, the journeys would still take decades or centuries. We have built machines that can escape the gravity of our world. We have crafted probes that can flee the pull of our own Sunday. We have achieved a technical mastery that would seem like magic to our ancestors. But we have never broken the tyranny of distance. We have only learned how to measure its true, terrifying scope. It is a realization that changes our perspective entirely. It forces us to look back, not just forward. If the stars are functionally unattainable, then this system, our system, is not a mere starting point. It is the whole arena. This collection of 8 planets, their moons, the asteroids and the comets in the distant dark, this is our inheritance. It is our entire universe in miniature. The great uncrossable void is not a failure of our imagination. It is a feature of our cosmos. It ensures that life, should it arise on a world, is given an entire solar system as its cradle, its laboratory, its home. We are not cosmic islanders dreaming of a mainland we can never reach. We are inhabitants of a continent of unimaginable richness, whose shores we have barely begun to explore. The challenge is not how to leave, but how to understand where we are. To map every corner of this vast, intricate, and beautiful home. To see the canyons of Mars, the methane seas of Titan, the cryovolcanoes of Triton, and the swirling storms of Jupiter not as stepping stones to the stars, but as destinations in themselves. As wonders of a universe we are privileged to inhabit. The dream of interstellar travel may be the ultimate expression of our desire to explore, to push boundaries. But the reality of interstellar distance teaches us a harder lesson, a lesson in humility, a lesson in patience, and a lesson perhaps in what it truly means to be home. Our solar system is not a cage. It is a sanctuary vast beyond our comprehension, and its exploration is a task for 1,000 generations to come. So the map is drawn, the true soul-crushingly vast map of our home. And with this terrible new knowledge, a question begins to smolder. It is a question that has fueled our dreams for a century. Can we ever leave? Not just for a brief visit to a neighboring rock, but to truly depart, to set a course for another sun, another possible Earth, to make the leap across the interstellar abyss. The romantic vision is of a sleek vessel slicing through the void, a craft that bends space and time to its will, arriving at Proxima Centauri in a matter of years. But the universe does not yield to romance. It yields only to physics. And the physics of interstellar travel presents a bill so steep It threatens to bankrupt our species' ambition. The first item on that invoice is energy, an amount of energy so stupendous it slips past our comprehension. To understand the chasm we face, we must first abandon our terrestrial intuition. The chemical rockets that lifted us from Earth are magnificent achievements. But in the interstellar ocean, they are like trying to cross the Pacific with a single firecracker. The energy locked in their fuel is a pittance. It is a measure of power fit for climbing a gravity well, not for crossing the light years. The governing principle here is the most famous equation in history. Einstein's terrifyingly simple statement that mass and energy are two faces of the same coin. To make something move, you must give it kinetic energy. To make it move very, very fast, a noticeable fraction of the speed of light requires an almost infinite rise in power. As you approach light speed, your vessel's mass effectively increases. It fights back against your every effort to accelerate it further. Each new increment of velocity costs more energy than the last. It is the ultimate law of diminishing returns etched into the fabric of space-time itself. Let's try to put a number on this. To accelerate a modest starship, perhaps the size of a large naval vessel, to just half the speed of light, you would require more energy than all of humanity has consumed in its entire history. Every fire ever lit, every lump of coal ever burned, every atom ever split in a reactor, every drop of oil ignited, all of it combined, just to get your ship up to speed. And then you face an equal and opposite problem. You need to spend that same colossal amount of energy again to slow down when you arrive. Unless your mission is simply to become a relativistic cannonball, atomizing on impact with your destination. This is not an engineering challenge in the way a bridge or a skyscraper is. This is a fundamental barrier of cosmic scale. Our most powerful machines are humbled by this reality. So, where could such power possibly come from? Scientists, in their brilliant optimism, have imagined solutions. One of the earliest was Project Orion, a vessel driven by nuclear bombs, a ship that would ride the shockwaves of atomic detonations. It is a magnificent, brutal, and terrifyingly clever idea. A train of hydrogen bombs would be ejected from the rear of the ship and detonated. A massive pusher plate shielded and engineered to withstand the fury of a sun would absorb the impulse. It would be a continuous series of controlled nuclear explosions punching the craft forward. Orion is perhaps the only technology we can conceive of with our current knowledge that could even begin to do the job. It could potentially reach 5 to 10% of the speed of light. This would cut the journey to the nearest star from 70,000 years down to a more manageable 40 to 80 years. But consider the vessel itself. It would need to carry thousands, perhaps tens of thousands, of nuclear devices. It would be a flying arsenal of unimaginable destructive potential. Its construction would demand a global effort, a marshalling of resources that would dwarf any project in human history. And even this, our most audacious plan, only gets you a fraction of the way there in a single human lifetime. What if we dream bigger? What if we could find the perfect fuel? Physics offers one candidate: antimatter. When a particle of matter meets its antimatter twin, they annihilate. They cease to exist, converting 100% of their mass into pure energy. It is the most efficient and powerful energy source permitted by the laws of the universe. A few dozen kilograms of antimatter could, in theory, propel a ship to near light speeds. The problem is not the theory, the problem is reality. Right now, at facilities like CERN, we can create antimatter. We smash particles together in colossal accelerators and painstakingly collect the exotic shrapnel. But the amount we create is almost nothing. If you took all the antimatter humanity has ever synthesized, it would not be enough to warm a cup of tea. To produce a single gram would require the entire energy output of our planet for hundreds of years, and its cost would be measured not in trillions, but in quadrillions of dollars. Then comes the even greater challenge: storage. You cannot put antimatter in a container. It would instantly touch the walls and obliterate itself, and the container in a flash of gamma rays. It must be held in a perfect magnetic vacuum, suspended, never touching anything. For a journey of centuries, this magnetic bottle cannot fail, not for a microsecond. A power flicker would mean the instantaneous violent end of your ship and everyone aboard. So antimatter, the ultimate fuel, remains a distant, almost mythical substance. Perhaps we are thinking about this all wrong. Perhaps the ship shouldn't carry its fuel at all. This is the logic behind concepts like the laser sail. Imagine an enormous, ultra-thin, highly reflective sail light years across. Here on Earth, or in our solar system, we construct a colossal laser array, an instrument the size of a continent focusing the light of 1,000 power plants into a single coherent beam. This beam of pure light crosses the void and pushes the sail. The gentle, relentless pressure of photons accelerates the craft over time. No fuel to carry means the ship can be incredibly light. In theory, such a system could accelerate a small probe to 20% of the speed of light. The journey to Proxima Centauri could shrink to just 20 years. It's an elegant, breathtaking vision. But here too the devil is in the details. The sheer scale. The laser array would be the largest machine ever built. Its power consumption would be equivalent to that of an entire nation. It would need to maintain a perfect, unwavering focus on a target trillions of kilometers away, an object smaller than a grain of sand as seen from Earth. And then there is the same old problem in a new guise: braking. How does the gossamer sail slow down from 20% of the speed of light? There is no giant laser waiting at the other end to push it back. The dream of relativistic travel, of shrinking the void, remains locked behind an energy wall, a wall so high and so thick that we cannot yet see a way through it or over it. And this realization forces us to confront a second, even more daunting proposition. If we cannot go fast, we must go slow. We must build not a vessel but a world, an ark, a generation ship. This is a machine designed not to outrun time but to endure it. A ship that will be home to generations of human beings who are born, live, and die in the void. People whose great-great-grandchildren might one day see the destination star brighten in their sky. The engineering challenges here pivot from the realm of pure physics to the tangled complexities of biology. You are no longer building a vehicle. You are attempting to bottle a planet. You must create an entirely closed and perfectly self-sustaining ecological system, a system that can support human life flawlessly for 1,000 years or more. Think about what that entails. Every single atom of water you bring must be recycled forever. Every drop drunk, every bit of vapor exhaled, every molecule used to grow food. It must all be captured, purified, and returned to the system without loss. A single unrepairable leak could doom the mission centuries into its journey. Every breath you take is the same. The carbon dioxide you exhale must be captured by plants. Those plants must release oxygen, which you then breathe. This delicate planetary cycle of respiration must be perfectly balanced inside a metal hull. On Earth, the biosphere is a vast, chaotic, and incredibly resilient buffer. Our atmosphere and oceans can absorb immense punishment. In a starship, the buffer is gone. The margin for error is zero. Then there is food. You cannot pack 1,000 years' worth of supplies. You must create a sustainable, regenerative agricultural system. This means soil with its trillions of microbes, a universe of complexity in every handful. It means pollinators, worms, fungi, the entire invisible architecture of life that supports our food chain. You need genetic diversity in your crops to guard against a single blight that could cause a total system collapse. A failed harvest is not a matter of economics. It is a mass extinction event for your tiny civilization. And what of waste? Everything from human effluents to machine parts must be broken down and reused. In this world, there is no away. You cannot throw anything away. Every discarded component, every fallen leaf, every molecule must be fed back into the system. Your ship is a sealed terrarium, a fragile bubble of life adrift in a sterile infinity. The International Space Station is our only current attempt at such a system, and it is a leaky, primitive, and constantly failing prototype. It relies on regular resupply missions from Earth to replenish its air, water, and food. Its life support systems are a constant source of maintenance headaches. Now imagine scaling that up to support hundreds or thousands of people and making it operate without fault, without resupply for 30 generations. It is an engineering problem of such staggering intricacy that it borders on biological alchemy. We do not know how to build a small, stable, man-made biosphere on Earth, let alone one that can survive a millennium in deep space. We are children trying to assemble a watch with sledgehammers blindfolded. The task requires a godlike understanding of ecology that we simply do not possess. And even if we could somehow solve the riddle of the perfect closed ecosystem, even if we could build this ark, it must still survive the journey through the wilderness itself. The space between the stars is not empty. It is a shooting gallery. For millennia, we have lived under a profound shield, a planetary embrace that has protected the delicate spark of life from the true violence of the cosmos. First, there is our atmosphere, a 100-kilometer deep cushion of gas. It burns up the vast majority of meteoroids before they ever reach the ground. Second, and far more important, is our magnetic field, an invisible force field generated by the churning molten iron core of our planet. It extends tens of thousands of kilometers into space, deflecting a constant lethal wind from our own sun. But its most critical role is shielding us from an even more insidious threat, galactic cosmic rays. These are not like the radiation we are familiar with from X-rays or nuclear power. They are the universe's shrapnel. They are atomic nuclei, protons, helium, and even iron atoms stripped of their electrons. Forged in the fury of distant supernova explosions, they are accelerated to nearly the speed of light. They rip through the galaxy like subatomic bullets. When one of these particles strikes a living cell, it is a microscopic cataclysm. It shatters DNA strands, carving a path of destruction. Our magnetosphere deflects most of them. Our atmosphere stops the rest. We are, by cosmic standards, living in a radiation-proof bunker. A starship has no such protection. Out in the interstellar medium, it is exposed to the full, unmitigated blast of this radiation, a constant, inescapable rain of high-energy particles from every direction at all times. Over the course of a centuries-long journey, the accumulated dose would be catastrophic. It would riddle the crew with cancers. It would cause sterility cataracts and severe damage to the central nervous system. It would degrade the ship's electronics, causing microscopic short circuits and system failures. It would slowly, inexorably poison the entire mission. So we must build our own shield. But how? The simplest solution is brute force, a thick hull. But to be effective against galactic cosmic rays, the shielding would need to be meters thick, surrounding your entire habitat with several meters of lead or other dense materials. This presents a familiar, soul-crushing problem. The sheer mass. The weight of the shield would be astronomical, making your ark unimaginably heavy, and a heavier ship requires exponentially more energy to accelerate, even to the slow speeds of a generation ship. The energy problem and the radiation problem are locked in a vicious feedback loop. Lighter materials like water or hydrogen-rich plastics are actually better shields per unit of mass. They are more effective at absorbing the energy of these cosmic bullets, but you would still need a shield of water many meters deep, encasing the entire vessel. a colossal flying aquarium just to keep the crew alive. The mass penalty remains monumental. What about a more elegant solution? An artificial magnetosphere? A system of powerful superconducting magnets that could generate a protective bubble around the ship just like Earth's. This is technologically plausible, but it would require a fantastic amount of energy, a powerful nuclear reactor running constantly for the entire duration of the 1,000-year journey. It would have to operate without a single critical failure, because if that magnetic field were to collapse, even for a short time, the crew would be exposed to a lethal dose of radiation. There would be nowhere to hide. The Ark, your perfect self-contained world, would become a tomb, sailing silently through the void, its delicate cargo of life, sterilized by the very cosmos it sought to explore. The universe it turns in is not a benign void. It is an actively hostile environment, and we are exquisitely fragile. Our biology is tuned to the gentle, forgiving cradle of a single planet. To leave it is to declare war on our own nature. And this brings us to the final and perhaps highest barrier. A barrier not of steel or energy or radiation, but of the mind. The human element. Let us assume we solve everything else. We discover a limitless source of energy. We master the art of building a perfectly closed biosphere. We devise a shield that can protect us from the cosmic onslaught. We build the Ark, we launch it into the darkness, and now the true journey begins. A journey not of distance, but of the human spirit. Imagine you are born on this ship. The concept of outside is an abstraction. The sky is not a blue expanse, but a metal ceiling hung with artificial lights. The only horizon you have ever known is the curving wall of your habitat. You have never felt rain on your skin or wind in your hair. You have never smelled a forest after a storm or the salt of an ocean. The entire sensory library of the human experience, built over millions of years of evolution on a living world, is denied to you. Your reality is a meticulously engineered, perfectly controlled, and utterly monotonous environment. And you know that your children will be born into this same reality, and their children after them. Your life has been given a single unyielding purpose chosen for you by ancestors you will never meet. You are a link in a chain, a biological component in a multi-generational machine. What does this do to the human psyche? How do you maintain morale, purpose, and sanity over 30 generations locked in a can? The initial crew, the ones who leave Earth, will be driven by the fire of exploration. But what about the 10th generation, the 15th? They will have no memory of Earth. It will be a myth, a story told on a screen. Their destination will be equally mythical. A paradise they may never live to see. They are stranded in the middle, in the endless, unchanging journey. The psychological pressures would be immense. The claustrophobia, the lack of privacy, the social friction of a small, isolated community. Every human flaw, jealousy, greed, lust for power would be amplified in this pressure cooker. How do you structure a society to withstand this? What form of governance can remain stable for a millennium? A democracy? A technocracy? A military command? What happens when a faction decides they no longer believe in the mission? What happens when a charismatic leader preaches that the ship itself is the whole universe and the legends of Earth and the destination are lies? How do you prevent the slow decay of knowledge, the loss of critical skills over centuries? The engineers of the first generation will be experts, but their children will be apprentices learning from textbooks and simulators. By the 20th generation, will they still truly understand the fantastically complex machine that keeps them alive, or will they be reduced to performing rituals and maintenance tasks they no longer comprehend? A society of caretakers tending a machine whose original purpose is lost to dogma and time. Then there is the grim calculus of biology. A small closed population is a genetic dead end. You would need a large and carefully selected founding crew, thousands of individuals, to avoid the catastrophic effects of inbreeding over many generations. This makes your ship even larger, more complex, and more resource-hungry. Every choice, from who is allowed to have children to what careers people can pursue, would have to be ruthlessly managed. Individual freedom would be a luxury the mission could not afford. The human spirit, with its messy, unpredictable, and glorious desire for self-determination, might be the very thing that scuttles the voyage. We are creatures of a planet. Our minds and bodies are tethered to it in ways we are only beginning to understand. The steady pull of its gravity, the rhythm of its 24-hour day, the changing of its seasons, these are not just poetic notions. They are the deep metronomes that have shaped our very being. To cut that cord is to conduct the most terrifying experiment in human history, an experiment to see if humanity can survive once it is removed from the only home it has ever known. The challenges cascade into one another. The physics demands a journey of millennia. The millennia demand a perfect biological arc. The arc demands a society that can withstand unimaginable psychological and sociological stress. It is a chain of cascading impossibilities. Each link in the chain is forged from the fundamental laws of the universe and the unchangeable truths of our own biology. This is the sobering reality of the interstellar dream. It is not a simple matter of building a better engine. It is a confrontation with the very essence of what we are and the universe we inhabit. The great silent gulf between the stars is not just empty space. It is a physical, biological, and psychological barrier of the highest order, a monument to the scale of the cosmos and the profound, beautiful fragility of us. We have felt the chilling whisper of the Kuiper Belt. We have charted the ghostly expanse of the Oort Cloud. We have measured the void that separates our sun from the next, and in doing so, we have come face to face with a truth so profound, so unyielding, it challenges our deepest identity. For millennia, we have defined ourselves as explorers, as pioneers. It is the singular narrative of our species. We crossed the savannas, we conquered the oceans, we climbed the highest peaks and touched the floor of the deepest trench. We broke the bonds of gravity and left footprints in the dust of another world. Each frontier was a challenge, a line drawn in the sand by nature, and each time we erased it. It is written in our myths, encoded in our DNA. The horizon is not a boundary, it is an invitation. So we look to the stars, those distant campfires in the cosmic dark, and we see the next ocean, the final greatest frontier. The question has always been when, not if. When will we build the ships to carry us to Alpha Centauri? When will we establish colonies in the light of alien suns? It feels like our manifest destiny, the logical endpoint of our journey. But the universe does not care for our narratives. The cosmos does not bend to the arc of human ambition. Physics is a merciless legislator, and its laws are absolute. And after all our calculations, after all our dreams and designs, we are now forced to confront the ultimate revelation. The final frontier is different. This time the barrier may be impassable. This time the invitation may have been a mirage. We have journeyed to the edge of our own solar system in our minds and with our machines. We have measured its scale and weighed its challenges. And the conclusion we must now face is as stark as it is humbling. Our sun, our family of planets, this archipelago of worlds, it is not our cradle. It is our forever home. And the story of humanity will be the story of the solar system. Because for us, for our fragile biology, for our fleeting lives, there may be no escape. Let us assemble the evidence for this final staggering verdict. Consider the case file on cosmic distance, the first great obstacle. We learned that our solar system, truly measured, ends halfway to the nearest star. A kingdom of ice and darkness, a trillion cometary ghosts in a spherical shell. The Oort Cloud. Our fastest emissary, the Voyager 1 probe, travels 1 million miles a day, a speed that feels almost mythical in human terms. Yet for that probe to cross its own solar system to exit the Oort Cloud would require a journey of 30,000 years, 30 millennia, and span of time that swallows the entirety of recorded human history. Every king, every empire, every pyramid, every poem, all would rise and fall and turn to dust in the time it takes our fastest machine to simply leave our sun's gravitational backyard. This is the opening statement in a case against our interstellar dream, and it is devastating. The distances are not merely large, they are a different category of reality. Our minds evolved to judge the arc of a thrown spear cannot process a number like 4¼ light years. That is the gulf separating us from Proxima Centauri. So we translate it. If our sun were a marble in New York City, Proxima Centauri would be another marble in Chicago. And in between, 1,000 miles of absolute near-perfect emptiness, nothing. No rest stops, no islands, no harbors, just a void more profound and more complete than anything we have ever known. A starship traveling at Voyager's velocity would take 75,000 years to cross that chasm of space-time between two marbles 1,000 miles apart. 75 millennia. A pilgrimage so long that the continents on Earth would shift. Ice ages would come and go. Our own species might evolve into something else entirely. The destination star itself, Proxima Centauri, would have drifted a significant distance across the galaxy in that time. You would be chasing a ghost. The target moves, the ship crawls, time erodes all purpose. This is the tyranny of distance. It is not a technological problem. It is a fundamental feature of the universe we inhabit. The cosmos is built on a scale that is hostile to impatience, and our species is nothing if not impatient. We live for decades, not eons. Our civilizations last for centuries, perhaps millennia, if they are fortunate. There is no frame of reference, no cultural or biological software we possess that can accommodate a project spanning 100,000 years. It's like a single bacterium on a beach, dreaming of crossing the Pacific Ocean. The sheer scale of the enterprise renders the ambition absurd. The very fabric of space-time is the first wall we face, and it is a wall of infinite thickness. It tells us that the space between the stars is not an ocean to be crossed, but a form of eternity to be endured, and we are not eternal, so we must go faster. That is the obvious solution, the engineers answer. We must build engines that can shrink the journey, taming those astronomical distances with breathtaking velocity. This brings us to the second exhibit in our case, the physics of motion. The relentless gatekeeper of cosmic travel is a principle called the rocket equation. It is a simple, elegant, and brutal piece of mathematics. It dictates that to go faster, you need more fuel, but that fuel has mass, so you need more fuel to push the fuel you're already carrying. This creates a vicious recursive cycle. The cost of every additional increment of speed grows exponentially. To reach just a fraction of the speed of light with chemical rockets, the kind that took us to the moon, you would need a fuel tank larger than the known universe. It is a mathematical impossibility, a categorical dead end. So we dream of more exotic solutions. We imagine ships powered by the very heart of the stars, nuclear fusion. A fusion rocket could, in theory, accelerate a craft continuously. It could achieve perhaps 10% of the speed of light, an incredible velocity over 60 million miles per hour. At that speed, the journey to Proxima Centauri is no longer 75,000 years. It shrinks to a more manageable 45 years, This is within the span of a single human life. The problem seems solved, the barrier is broken, but the universe is subtle and its laws have hidden clauses. To maintain the fusion reaction for that journey, you need a stupendous amount of fuel like deuterium or helium-3. And you must contend with the rocket equation's cruel logic once more. To slow down at the destination, a rather critical part of any visit, you need to burn just as much fuel as you did to speed up. Your ship must be more than 95% fuel at the start of its journey. The actual payload, the habitat, the crew, the science instruments, is a tiny, fragile afterthought, a speck of dust on a mountain of propellant. And we haven't even touched upon the engineering. Containing a star inside a magnetic bottle for half a century, while it hurls you through the interstellar medium, is a task for a civilization far beyond our own. It is a godlike level of energy management. What about other, even more fantastic ideas? Beaming a starship across the void on a powerful laser sail. The energy required for the laser array would equal the entire current power output of human civilization, focused for decades on a single point in the sky. And again, how do you stop? You would need another colossal laser array waiting for you at Proxima Centauri, built by whom exactly? The logistics spiral into paradox. And then there is the ultimate dream antimatter, the most efficient fuel permitted by physics. The complete conversion of matter into pure energy. An antimatter drive could theoretically push a ship to 90% of light speed or more. The journey to our nearest stellar neighbor could take just 5 years. But antimatter is the most volatile, most dangerous substance imaginable. A single gram of it touching normal matter releases the energy of a strategic nuclear weapon. A starship would need tons of it. It would be a vessel constructed around a bomb of unimaginable power. The slightest malfunction, the tiniest leak, a single stray cosmic ray hitting the containment field, and your ship does not just fail. It vanishes in a flash of gamma rays that could sterilize a planet. And where do we find this material? We must manufacture it atom by atom in particle accelerators. To create a single gram of antimatter with our current technology would take the entire energy output of our planet for over 100,000 years and cost more money than has ever existed in human history. We are talking about quadrillions upon quadrillions of dollars. The economics of interstellar travel are as daunting as the physics. Even if we could conjure such a machine from our dreams, we would slam into the universe's ultimate speed limit, the velocity of light. You can approach it, you can get tantalizingly close, but you can never reach it. As you accelerate, your mass increases infinitely. Time aboard your ship slows to a crawl relative to the universe you left behind. This is Einstein's special relativity, and it is the final cruel twist. You might make the trip to a star 50 light-years away. For you aboard the ship, perhaps only a decade passes. You arrive youthful and triumphant, but when you look back at Earth, you are looking at a ghost. Centuries, even millennia, have elapsed. Everyone you knew is gone. The language you spoke may be dead. The civilization that sent you might be a forgotten chapter in a history book. You have not traveled to another star. You have traveled to another time. You are an exile, a relic, a castaway in the future. This is not exploration. It is a form of suicide. The laws of motion do not just make interstellar travel difficult. They rig the game so that even if you win, you lose everything. But let us assume we overcome all of this. Imagine a future where by some miracle of science and engineering we construct a vessel that can bridge the celestial gulf in a single lifetime. We solve the propulsion problem, we manage the fuel, we accept the strange paradoxes of relativistic time. Now we face the third and perhaps most insurmountable barrier of all, ourselves, our own fragile, complex and utterly terrestrial biology. We are not made for the cosmos. We are creatures of the earth. Every cell in our bodies is tuned to the specific conditions of this world. Our evolution took place in a warm, wet environment, shielded by a magnetic field, bathed in a thick atmosphere, and anchored by a constant, gentle pull of gravity. The universe beyond our planet's embrace is not merely empty. It is the most hostile environment imaginable. The first killer is radiation. Our sun and the galaxy at large bombard space with a ceaseless storm of high-energy particles, cosmic rays. The nuclei of atoms, stripped of their electrons, accelerated to near light speed by ancient supernovas. They are subatomic bullets. Here on Earth, our magnetosphere and atmosphere form a planetary shield, deflecting and absorbing this lethal barrage. In deep space, there is no shield. These particles will pass through the hull of a starship as if it were tissue paper. They will shred DNA, triggering cancers and cellular breakdown. They will damage brain tissue, leading to cognitive decline, memory loss, and early onset dementia. To adequately shield a crew for a multi-decade journey would require a barrier of lead or water many meters thick. This adds thousands upon thousands of tons of mass to the ship, throwing us right back into the merciless arms of the rocket equation. More mass means more fuel, which means a bigger ship, which needs more shielding. The problem compounds itself into impossibility. The second silent destroyer is the absence of gravity. Our bodies are in a constant fight against the pull of the Earth. Our bones maintain their density, our muscles their strength, because they have a force to push against. In 0G, the body begins to deconstruct itself. Bone density leaches away at a terrifying rate. Muscles atrophy. The cardiovascular system weakens as the heart no longer has to pump blood uphill. Even the eyeballs change shape, impairing vision. Astronauts on the space station must exercise for hours every single day just to slow this relentless decay. Now imagine that state not for a year but for 50 years. No amount of exercise can completely halt this process. By the time you arrived at your destination, you would be a fragile creature with the bones of an advanced osteoporosis patient, a weakened heart and compromised senses. You would be in no condition to step out onto a new world. You might not even survive the gravitational forces of your destination planet. You would have traveled across the stars only to be crushed by a new gravity. But the most profound challenge may not be physical but mental. The human mind is not built for absolute isolation. We are social creatures shaped by open skies, changing seasons, and a rich sensory world. Picture the psychological reality of an interstellar journey. You are sealed in a small metal container, a box. Outside your window is a blackness, so complete, so unchanging, it defies comprehension. The stars do not twinkle, they do not move, they are hard, sharp, indifferent points of light for 40 years. Your entire world is a handful of other people, the same faces every day, the same corridors, the same recycled air. There is no escape, there is no fresh air. There is no horizon, there is no away. The psychological pressure would be unimaginable. The generational ship, a favorite trope of science fiction, is perhaps the most terrifying prospect of all, a society born in a can. Generations living and dying in transit who never knew a sunrise, never felt rain, never saw a true sky. They are prisoners from birth, their only purpose to fulfill the dream of long-dead ancestors. What kind of culture would emerge from such an existence? What resentments, what mutations of belief? Would they even remember the purpose of the journey by the 1000th year? Or would the ship simply become their entire universe, its mission, forgotten its destination, a myth? It is a sociological and psychological experiment on a scale too horrific to contemplate. We are biological beings bound by the needs of flesh and blood and mind. We are a product of Earth, and like a deep-sea fish brought to the surface, we cannot survive in the alien pressures of the cosmos. Our bodies are the final prison. a prison of bone and blood more confining than any rocket equation, more impassable than any light year. So this is the final inescapable synthesis. The distances are too great, the physics of travel are too punishing, and our own biology is too fragile. These are not separate problems. They are a single interconnected wall. To survive the radiation, you need more shielding. More shielding adds mass. More mass requires more powerful engines and more fuel, which we cannot build. To shorten the journey time, to save the crew's biology, you need to travel at relativistic speeds. But this requires impossible energies and exiles you in time. Every solution creates a new insurmountable problem. It is a Gordian knot with no sword sharp enough to cut it. This is what leads us to our profound and difficult conclusion. Humanity will likely never leave the solar system. Our machines will, our robotic emissaries, the children of our minds. They are unburdened by the tyranny of the flesh. They can be shielded, they can be patient. Time is meaningless to them. Voyager, Cassini, Perseverance, Hubble, these are the true explorers of the cosmos. They are our eyes, our hands, our senses extended across the void. They will be our ambassadors to the stars. They will carry our greetings, our science, our art. They will drift through the silent canyons of interstellar space for millions of years, long after our civilization may have vanished. That is how we will explore the galaxy, at a distance, through our proxies. But for us, for humankind, our destiny is here. And this is not a tragedy. It is not a declaration of failure. It is a moment of profound clarification. For centuries, we have seen the solar system as a stepping stone, a mere starting point on a journey to the galaxy. This realization forces us to see our home in a new light. This is not the shore of the cosmic ocean. This is the ocean itself. Our solar system is not a small confining cradle. It is an astonishingly vast and diverse archipelago of worlds. There are more wonders here than we can explore in 1,000 generations. There are the canyons of Mars, 3 times deeper than our own Grand Canyon. There are the liquid methane seas of Titan under a nitrogen sky, the subsurface ocean of Europa, which may hold alien life, the metallic core of a shattered protoplanet orbiting as the asteroid Psyche, the geysers of Enceladus, the storms of Jupiter, the rings of Saturn, the ice giants Uranus and Neptune still shrouded in mystery, the trillion comets of the Oort Cloud. This is our inheritance, a collection of worlds more fantastic than any science fiction writer ever dreamed. We have spent so long looking at the distant stars that we have failed to truly appreciate the kingdom we already inhabit. Perhaps our destiny was never to conquer the galaxy. Perhaps it was to become masters of our own solar system, to understand its worlds, to visit them, perhaps even to live on them, to build a civilization that spans from the heat of Mercury to the ice of Pluto. This is not a lesser destiny. It is a magnificent one. It is a project for the entire future of the human species. The universe is not shrinking for us. Our perspective is expanding. We are not prisoners of the sun. We are children of the sun, and this is our home. Its sheer breathtaking scale does not trap us. It challenges us to be worthy of it. And for the foreseeable future of our species, it is everything. It is our beginning, our middle, and our end. It is our entire universe. And so the journey ends, not with a triumphant arrival at a distant star, not with humanity spreading across the galaxy, but here, right here, we have traversed the colossal distances of our own cosmic backyard, from the sun's fiery surface to the ghostly twilight of the Oort Cloud. We have measured the void, calculated the energies, and faced the tyranny of time, and the conclusion is as inescapable as the gravity that holds us. The verdict is in. This is it. This solar system in all its immensity is our universe. The stars, those tantalizing diamonds on black velvet, are not destinations, they are fixtures on the walls of our home. A home with a fence 100,000 times farther than the sun, but a fence nonetheless. Does that feel like a failure? Does a shadow of disappointment creep into your soul? For generations we have been a species that looks up and dreams of going. Our stories, our ambitions, our very definition of a future, they have all been predicated on the idea of elsewhere, of starships whispering between nebulae, of new suns rising on alien shores. We imagined ourselves as cosmic pioneers destined to inherit the galaxy. It is a beautiful, intoxicating, and profoundly human dream, and we have just spent an hour confronting the physics that shatter it, the sheer brutal arithmetic of space that laughs at our chemical rockets, the lethal radiation that scours the interstellar void, the millennia that would pass turning starships into tombs. It feels like a closing door, a final definitive statement. You are here to stay. The great cosmic ocean is before you, but you have no vessel to cross it. You are and will remain an island civilization, confined to a single isolated archipelago of worlds orbiting a single ordinary star. Is this then a story of limitation? A tragic tale of a species with boundless imagination and a brutal reality? Perhaps. Or perhaps we have been blinded by the glare of the distant stars. Perhaps in constantly looking out, we have failed to truly see what is in. What if we have been asking the wrong question all along? The question isn't, how do we escape? The question is, what have we failed to appreciate? What if this confinement isn't a prison but a gift, a chance to stop dreaming of a million abstract worlds and start exploring the 8 concrete ones, plus countless smaller wonders that we have been given? What if the solar system is not a cage but a garden of unimaginable diversity, a laboratory of cosmic processes waiting for us to discover its secrets? A legacy so vast, so rich, so mysterious that it could occupy the entire future of our species. Let us re-examine our home then, not as a starting point, but as the destination. The final frontier is not out there, it's right here. Look again at the worlds we thought we knew. Think of Mercury, the scorched inner sentinel. We dismissed it as a dead, pockmarked rock, but it is a world of impossible extremes, a testament to cosmic survival. Its iron heart, anomalously huge, generates a magnetic field, a ghost of a defense against the solar wind that should have stripped it bare. In its polar craters, in permanent shadow, there is ice, water frozen for billions of years, just a stone's throw from the solar furnace. Why Mercury is not a simple cinder. It is a planetary riddle holding clues to the violent birth of all inner worlds. And then there is Venus, our so-called twin. It is not a sister world, it is a cautionary tale, a vision of what happens when a climate slips into a runaway catastrophe. Its crushing acidic atmosphere hides a volcanic surface we have barely glimpsed, a world where it rains sulfuric acid, and the pressure can pulverize steel. To understand Venus is to understand the fragility of paradise. To map its hidden continents and decipher its atmospheric chemistry is to arm ourselves with the knowledge to protect our own world. It is a difficult, dangerous, vital quest, a challenge that could define a generation of explorers. And Mars, the red planet. For so long, the great hope for a second Earth, we dream of cities under Martian domes of terraforming its rusty plains. But this dream overshadows a more profound reality. Mars is a planetary fossil. It is a frozen museum preserving a chapter of history that Earth has long since erased. Evidence suggests that billions of years ago, it had rivers, lakes, perhaps even an ocean. It had a thick atmosphere and a protective magnetic field. It had for a fleeting moment all the ingredients for life. So where did it all go? What cataclysm silenced an entire world? The search for life on Mars is not just a hunt for microbes in the dust. It is a search for our own past, for the ghost of a second Genesis. To walk the dried riverbeds of Mars, to drill into its polar ice caps, is to perform an autopsy on a dead planet. To find out if we are alone, or if life once flickered next door, and if it did, to learn the terrible lesson of how easily it can be extinguished. This is not a sideshow. This is one of the most fundamental investigations humanity could ever undertake, and it is right here in our own system. We have spoken of the gas giants Jupiter and Saturn as impassable barriers, but this perspective is flawed. They are not obstacles, they are empires. Each one is a solar system in miniature, a gravitational monarch ruling over a court of dozens, even hundreds of captive moons. They are realms of such complexity that they defy our understanding. Consider Jupiter, the colossal king. Its great red spot is a storm that has raged for centuries, a vortex so large it could swallow our entire planet without a trace. We do not understand its power source, its depth, or its longevity. Beneath those swirling cloud tops lies an ocean of liquid metallic hydrogen, a substance that does not exist naturally on Earth, generating a magnetic field so powerful it creates auroras 100 times brighter than our own. A field that traps a torus of lethal radiation, a donut of death, encircling the planet. Jupiter is not a planet in the same sense as Earth. It is a failed star, a body on the threshold of nuclear fusion, a thing of unimaginable power and violence, and we have only just scratched its surface. And what of its moons? These are not mere satellites, they are worlds. Worlds as diverse and compelling as any we could imagine around another star. There is Io, the most volcanically active body in the entire solar system, a world perpetually torn apart by Jupiter's immense gravity. Its surface is a constantly repaved canvas of sulfur, fire, and brimstone, a heavy metal nightmare of a world beautiful in its ferocity. And then just next door in that same gravitational vice is Europa, a world wrapped in a shell of pristine ice. But beneath that frozen crust, the same tidal forces that torture Io are gently warming Europa's core, creating what scientists believe is a vast global ocean of liquid water, an ocean that may have existed for billions of years, an ocean that could contain twice the amount of water as all of Earth's oceans combined. It is dark, it is deep, it is ancient, and it might be the most likely place to find extraterrestrial life in our cosmos, not as a fossil but as a living, breathing biosphere, swimming in the eternal night beneath a ceiling of ice. The quest to drill through that ice, to send a submarine into the alien abyss of Europa, is arguably the single greatest adventure of exploration left to us. It is a journey that makes climbing Everest or sailing our own oceans seem like a walk in the park, and it is waiting for us in our own solar system. Think of Saturn, the jewel of the night sky. Its rings, which appear so serene and solid from afar, are a chaotic, dynamic, and breathtakingly complex system. They are not permanent, they are an ephemeral spectacle, a blizzard of countless ice particles from the size of dust motes to mountains, each in its own perfect orbit. Shepherded by the gravity of tiny shepherd moons, rippled by the passage of larger ones, raining down onto the planet's atmosphere destined to vanish in 100 million years, a cosmic blink of an eye. We are lucky enough to be alive when this wonder exists. To study it, to understand its origins and its fate, is to witness the celestial mechanics of creation and destruction firsthand. And Saturn's moons are just as strange and captivating. There is Enceladus, a tiny snowball of a moon, but it is alive. Great plumes of water vapor and ice crystals erupt from its south pole, geysers that blast material from a subsurface saltwater ocean directly into space, an ocean we can sample without ever landing. A probe can fly through those plumes and taste the chemistry of a hidden sea. It is an invitation from the cosmos, a message in a bottle sent to us. It says, here is an accessible alien ocean. Come and see. And then there is Titan, perhaps the most alien yet hauntingly familiar world we have ever seen. Larger than the planet Mercury, the only moon with a thick, substantial atmosphere. An atmosphere of nitrogen and methane shrouded in an orange organic smog. And on its surface it is cold enough for methane to exist as a liquid. It rains methane from the sky. That methane carves river channels, flows into vast lakes and seas. The Huygens probe landed on its surface with a squelch on the damp floodplain of an extraterrestrial river. Titan is a twisted reflection of Earth, a world of liquid, of weather, of geology, but with a completely alien chemistry. Could some form of life exist there? Something that breathes hydrogen and metabolizes acetylene? We don't know. The possibilities are so profound they border on science fiction. But Titan is real, and it is ours to explore. We push farther out to the ice giants Uranus and Neptune, the forgotten worlds visited only once decades ago by a fleeting flyby. Uranus, knocked on its side by some ancient titanic collision, rolls around the sun like a barrel. Its faint rings are dark as coal. Its moons are named for characters from Shakespeare. It is a place of deep, serene, sapphire mystery. What secrets are locked in its bizarre, sideways magnetic field? What chemistry churns in its frigid atmosphere of hydrogen, helium, and methane ice? We know almost nothing. It is a brand new continent waiting for its Magellan. Neptune, its deeper blue cousin, is a world of unimaginable violence, home to the fastest winds in the solar system, screaming at over 1,000 miles per hour. Great dark spots, storms the size of Earth, appear and vanish in its atmosphere. And its largest moon, Triton, is a captured object from the Kuiper Belt, a world in a slow-motion death spiral orbiting the planet backwards. Its surface of frozen nitrogen is scarred by dark streaks from cryogenic geysers, ice volcanoes that erupt plumes of nitrogen frost and dark organic compounds. It is a preview of the strange frozen realm that lies even farther out. Beyond Neptune, we enter that realm, the Kuiper Belt, the solar system's attic, a junkyard of creation containing hundreds of thousands of icy bodies, the leftover building blocks of the giant planets. We once called Pluto the last planet, a lonely outpost. Now we know it is just the first, the brightest citizen of this third zone of our solar system. And what a world it is. A dwarf planet with mountains of solid water ice capped with frozen methane snow. Vast plains of nitrogen ice that form convection cells like a simmering pot. A thin bluish atmosphere. And a giant heart-shaped glacier. It is a world that is shockingly, beautifully, geologically alive. When we thought it would be a dead, inert snowball, Pluto broke all the rules. And it is not alone. There is Eris, more massive than Pluto, Makemake, Haumea, Sedna on a bizarre elongated orbit that takes it nearly 1,000 times farther from the Sun than the Earth. Each of these is a world in its own right, each one a pristine 5 billion-year-old sample of the primordial solar nebula. To explore them is to engage in a form of cosmic archaeology, to read the original recipe of our own home. This is a realm so vast and so populated it would take thousands of years and thousands of missions to even begin to catalogue it. And this is all held together by the Sunday hour star. We think of its gravity as our jailer, but it is our architect, our engine, our lifeblood. It is the anchor that gives our entire cosmic neighborhood its structure. Its light and heat are the energy that drives the weather on Earth, the geysers on Enceladus, the sublimation of comets. Every atom in our bodies heavier than hydrogen and helium was forged in the heart of a star that died long before our sun was born. Our sun is a second-generation star. It is a recycler of cosmic dust. It built this home for us from the ashes of its ancestors. To be bound to it is not a sentence, it is a connection to the very fabric of cosmic history. So we find ourselves back where we started, on this small, fragile blue world, and the realization of our confinement delivers one final profound message. This is it. This is everything. This planet is not a cradle we are destined to leave. It is the flagship of humanity, and it is the only one we will ever have. This truth elevates our responsibility from important to sacred. If there are no new Earths to escape, to no galactic empires to build, then the preservation of this one world becomes the ultimate human project. The challenge of our time and of all time to come. Exploration will not die. It will be transformed. Our destiny is not to conquer the galaxy, it is to become masters of our own garden, to understand the intricate connections between these worlds, to plumb the depths of the European Ocean, to walk the shores of Titan's methane seas, to decode the climate of Venus and the history of Mars, to build a sustainable multi-planetary civilization not as a stepping stone to the stars, but as an end in itself, to build a network of knowledge, presence, and understanding that spans the entire breadth of the sun's embrace. This is a destiny grand enough for any species. Look up at the night sky one last time. The stars haven't changed. They still glitter with the same cold, distant fire. But perhaps your perspective has. They are no longer unfulfilled destinations mocking us with their distance. They are the view, the magnificent, unchangeable, breathtaking wallpaper in the house we will never leave. And in this house there are more rooms than we could ever hope to explore, more mysteries than we could ever solve, more wonders than we could ever imagine. Our journey to the stars is over. But our journey through the solar system, that has just begun.